Good morning. Last class we started a new topic, a new chapter, that is on iron carbon phase diagram, and we have so far looked at this allotropic transformation, looked at the solubility of carbon in iron. We talked about a metastable phase, iron carbide, that we get in the system, and we also said that this is not the stable phase. Stable phase is graphite, stable form of carbon is graphite. So, today we will look at a bit deviate, we will look at iron graphite diagram also, but the process of decomposition of cementite to graphite is very slow, and in most materials of commercial importance, we in iron carbon alloy we do get carbide. Carbide is the form in which mostly carbon is present in steel. We looked at invariant reactions, and we have looked at iron cementite phase diagram. Today, we will see what happens if cementite breaks down, how does the carbide diagram changes, and then we also looked at microstructure of steel and a part of cast iron where carbon is present as cementite. Today, we will see what happens if this cementite breaks down into graphite and we get another type of cast iron called grey cast iron. We will look at that, and then we will try and interpret what is the effect of transformation temperature or cooling rate on microstructure that you get in steel, and introduce a new concept, a new diagram called time temperature transformation diagram. Now, let us look at this phase diagram. This farm line is what we looked at, we discussed in the last class, and here each of these points which are marked, they have definite composition. Like here we say that this is point 02, this part is cementite, here carbon is 6.67, this portion it is liquid, this is where you have austenite, and this is where you have delta ferrite, and this is the region terminal solid solution. This is the part you have alpha, here you have gamma plus liquid, here you have liquid plus cementite, and here you will have two phases primarily ferrite and cementite, but the way they are distributed, the structures are quite different. As you move from this region to this region to this, each of these regions you have different structures, structural features, and looking at the structural features of iron carbon alloy, it is possible to guess what is the amount of carbon present in the iron carbon alloy. Now, as I said, as has been mentioned, this is a metastable phase, and if you keep it at the system remains at high temperature for sufficiently long time, this type of decomposition takes place. And in fact, in many of these materials, particularly steel, which are used in power plants and also in petrochemical industries, where the steel is exposed to higher temperature during service, and people have looked at microstructures of such material after 20-25 years of service, and there they find that cementite has broken down into ferrite and graphite. So, that means that shows that prolonged holding at high temperature, the it is possible that cementite will break down and you will have graphite, and tendency for this graphitization is high as you move towards the higher carbon content. And in this diagram we have certain lines. So, these are the dotted line shows that these are the equilibrium line. Say if that eutectic, it is slightly different, more or less the eutectic temperature is maybe slightly higher, maybe 10 degree higher than this. Say if it is 11, I think 47, this is 1154, this is 723, this is around 734. So, something like that. This point is 0.8. So, in a graphite eutectic, this is slightly this side 0.7. So, more or less we can say that same diagram, it is possible to interpret the microstructure if graphitization does take place, and it is most prominent in the higher as the carbon content goes high. And there are certain high carbon alloys which are known as cast iron. Cast iron, they have carbon content, percentage carbon is much greater than 2, and particularly if it is around 4 or more, 4, 4.5 or beyond. So, there are many cast iron where you have carbon of this much order, and there the graphites are present, the cementite breaks down and graphites are present like flakes like this. So, say flaky graphite, and this you can see only by polishing, you need not etch. Normally, to examine a microstructure, you polish the surface, make it scratch free, shining, and then you etch. And while etching, it attacks certain phases and particularly the boundaries, and then the structure becomes visible. But in case of cast iron, where carbon is present in the form of graphite and its luster is so drastically different that even without etching, these graphite flakes or graphite morphology will be visible. So, these are whatever see is unetched structure, and this depending on the size and this morphology of this graphite flake can vary. It can be long, it can be short, something like this. It can also, by controlling the process of solidification and some inoculation treatment in certain forms of graphite cast iron, it is possible to get graphite in nearly this kind of a nodular shapes, round. So, difference is if a material has this kind of a flaky structure, they are like fine micro cracks. So, these properties that you expect, they will have poor tensile strength, the tensile strength will be poor, fracture, they will fracture easily, that fracture toughness will be very low, but presence of this kind of a graphite phase, it gives cast iron a very good property called damping property. So, therefore, it is a very commonly used material for construction, where you do not subject a material that material is not subjected to tensile stress, but compressive strength. It has good compressive strength, no doubt, and you need damping resistance. Say suppose the turbine bases, where the turbine is supported, or machine bases, they are made up of this type of grey cast iron. And nodular cast iron, if you can control its morphology, here this notch effect is less notch effect. So, less notch effect. So, therefore, here the chance of crack propagation that is little less. So, this form of iron is also known as ductile iron. So, that means by controlling the morphology of graphite in this cast iron, which is a form of cast iron where carbon is present as graphite, is called gray cast iron. The term gray derives from the nature of the fracture. If you look at a white cast iron where the cementite is where this carbon is present at cementite, and if it is quite brittle, and there the fracture appears to be very shiny. So, that is called white cast iron. If you look back here, this farm line says that it is the iron cementite diagram. So, these are the region, if it is present in the form of cementite, carbon is present in the form of cementite. So, these are white cast iron. We did look at its structure in the last class. As against that, the graphite morphology is more stable, and this type of cast iron has good damping capacity and good compressive strength, but poor tensile strength and low fracture toughness. Now, let us look at so that means that properties of iron carbon alloy is significantly that carbon is a major alloying element which defines the nature of this or the properties of iron carbon alloy. For example, in the steel regime, this portion is steel, and here if you look at under normal that structure that you get, we will later come about special types of heat treatment where properties can be changed substantially, but normally air cooled or furnace cooled steel, that means where the structure is more closer to equilibrium, which is described by this phase diagram. There you will find, if you increase the carbon content in this portion, there will be a slight because of the solubility it increases slightly, and then this part it is a linear, and then here around this almost you get that optimum property, and thereafter this property increases very slightly. So, this is you can say tensile strength. If you measure hardness, is very commonly this hardness also increases linearly in this part, where this is called hypoeutectoid steel, eutectoid steel. So, here this portion it more or less increases linearly, and cementite is quite hard, but thereafter the hardness increases is not much, I mean slight increase is there, but the ductility, look at the ductility. So, here as the strength increases, ductility goes down. So, carbon is the alloy element which controls the properties of steel to a great extent, and bulk of the steel are for most application like car body, they are very low carbon steel, they will be almost close to this end, which will be mostly ferrite, little pearlite, and you have rails, and these are medium carbon steel, say maybe 0.6, 0.7, these are the steel is a rail steel, and say cutlery and then hacksaw, these razor blades etc., they will have carbon content around 1.4. This is a razor blade. or hacksaw, razor blade, or tool steel will be somewhere in this region, whereas the. So, that means by controlling the carbon content you can get different types of property, very high hardness, and later on we will see by controlling cooling rate it is possible to change these properties to a much higher extent. I think next diagram here, this typically shows, I mean whatever I talked about, you look at this with a carbon content. I took this data from handbooks for steel which are cooled at a very slow rate, anneal steel, and these are, this axis gives either Brinell hardness is shown by this. So, look at this part, the hypoeutectoid steel, it is very strongly dependent, but thereafter the change is not much. This is yield strength, more or less at 0.8% it becomes maximum, and this is the UTS. Here also around 0.8% it becomes maximum. So, in fact, eutectoid is a structure, eutectoid steel, the structure is a good mixture of is a very fine mixture of ferrite and cementite. Cementite is harder, and this type of fine mixture gives or you can see that optimum properties, that is maximum possible yield strength or a tensile strength, but beyond that if at all the strength and hardness increases, that increase is marginal, but definitely the ductility will be much lower. As the ductility, as you go this side, which is not shown, the ductility plot possibly will fall like this. Now, let us look at the structure of this eutectoid steel critically. Last class we looked at that if you cool a steel from this austenitic region which has a carbon content which corresponds around 0.8. So, this is the eutectoid point. What happens as you cool at this eutectoid temperature around 723, as you go below this 723 degree centigrade, you have a precipitation, I mean this austenite breaks down simultaneously into a fine mixture of ferrite and cementite, and this is called perlite. And this perlite, we have seen that here that perlite, as has been mentioned, you have a cementite particle nucleating, a plate of cementite nucleates, it takes up 6.67% carbon. And where does this carbon come from? It will come from the surrounding region. If it comes from the surrounding region, the nearby region gets depleted of carbon and it forms ferrite. And when this ferrite grows, it rejects carbon, this carbon goes to the interface, you have another plate of cementite nucleating, and this is how the process continues, and it grows in this direction and it will also grow in these direction as well, until it encounters another particle or another similar colony of perlite in the structure. So, this is how this perlite forms. This is the perlitic structure. This is called perlite. Perlite, mind you, it is not a phase. It is made up of alternate layers of ferrite and cementite, and we saw that around this the width of this ferrite plate is around, if it is 7, then cementite width of the cementite is around 1. So, they will be in this ratio 7:1, and which comes directly, you can derive it directly from the composition points which are given in the phase diagram. Now, let us see what we do. We take a piece of steel, keep it in a furnace, and then what happens? We cool it to a particular temperature and try and follow how does the microstructure change take place, because here you have to allow time. We looked at the process here. Once the cementite nucleates, it has to nucleate by when the cementite precipitates out, it takes carbon from the side. So, carbon has to move. So, that means you have to allow time for movement of carbon atom and diffusion, and we have also seen that diffusion is a strong function of temperature. And but we also need to provide another activation, that means when a cementite plate forms, it creates a new surface. So, for that we need a driving force, and this driving force is provided by the degree of supercooling. If you cool more, then the driving force is higher. So, that means nucleation of this cementite particle will be faster. Chance of nucleation of cementite particle will be higher. So, that means there are two competing factors. One, you need a driving force to drive the reaction. Second, you have to allow time, or you have to control the temperature, which will allow the carbon to diffuse to form cementite. And this is what we see in this. So, this is the pictorial representation of that how eutectoid structure, that parlitic structure forms. This is ferrite, this is cementite. Now, suppose you take a piece of steel, we put it in a furnace, a bath, which is maintained at 760 degree centigrade, which is little higher than the eutectoid temperature, and we keep it for sufficient length of time, so that this piece attains uniform temperature from surface to the center. And we assume that the size of this sample is very small, and then what we do after keeping it for sufficient time, we transfer this to a bath maintained at 700 degree centigrade, which is little lower than the eutectoid temperature. And then after keeping it, then we monitor the time. After keeping it for a time t, we transfer it to another bath at room temperature. Maybe we quench it to room temperature, maybe we quench in water, and then we measure hardness and we polish the sample and etch and look at the microstructure. And we can repeat this experiment by maintaining the bath at 700 degree centigrade, and say suppose another sample we take transfer, we keep it for a time greater than the earlier previous time, and then we can have a series of sample which has been kept here and then transferred, then quenched to room temperature, and then let us measure their hardness and microstructure. And then we will see that if you measure the hardness, in one case if you draw the microstructure, you will find that it will be very difficult to etch. We will look at its structure little later, and its hardness but is very high, it is 64. That now Rockwell C scale hardness, if and steel, the Rockwell C scale is a very popular hardness scale, which we learnt in our earlier classes, the method of measuring hardness. And next look at another which has been kept for a little longer time, and here you see some nodules of this lamellar structure is forming, alternate layers of the ferrite and cementite, and when these nodules are growing, so this they etch very easily. So, this you can see, and this will etch very lightly, and we will see that its microstructure little later. And this type of process, and as the amount of this perlite increases, you will find that the hardness decreases. Here it is RC50. You keep it for little longer time, you will have more number of such nodules, and you will find its hardness is still less. And this type of experiments if one does, and then if one looks at the data, say you prepare a table or you make a plot, let us say, if you make a plot, say first, how does at a particular temperature, say suppose this is the intermediate bath has temperature T1, and in that case what we have seen, the first sample when you quench after certain time you get the maximum hardness, and this is around 64. Say this is what we have seen here, this is around 64, and maybe the second sample also, the first sample is 64, second sample also 64. After some time you may find that this is say little less, say this is say 60, then you get say somewhere 55. So, this is how it will go on, and maybe somewhere here it goes to maybe RC 20. And then if you join these points, you will get a plot like this, a sigmoidal kind of plot. Similarly, if you look at that microstructure and try to find out the percentage of that perlite nodule, and then you will find here also you will get a similar structure. Initially, if you remember that previous slide, here there is no perlite. So, for certain cases there is no perlite here, no perlite, and then that percentage perlite goes on increasing, maybe here it is 10%, here it is 50%, and here it is 100%. And here also if you join this point, you get this type of a sigmoidal curve, and then what you do from here, you try and find out from where it starts deviating from this peak value. Then we say that this is where that decomposition of austenite, say the main transformation is austenite is decomposing into perlite. So, this type of structure, this is called perlite. So, formation of perlite starts from here. So, this we can say that T s, that transformation, perlite transformation, that is begins at this temperature, and similarly where it reaches 100%, that lowest hardness value, we say that here the transformation is complete. And we do the similar experiment that you have done by keeping that intermediate bath at T1. We repeat the same experiment at another temperature T2, and there also you exactly do the same thing, and here you find that although this temperature, this part it still say 64, you will find here that hardness increases, say maybe from 20 it becomes say 35. We will see why it becomes harder. And then here also you try and find out the time at which the transformation begins or starts, and time when the transformation is over, that is finishing time. And similarly, that percentage perlite from microstructure also, looking at the microstructure also you can do the same thing and do another temperature and repeat this for a number of temperature T1, T2, T3, T4 and all. And then what you do? You compile a table. If you compile a table at different temperature, that is how does austenite decomposes into a mixture of ferrite and cementite. So, for this temperature T1, say start temperature, you get some number. So, maybe say you may find say this may be say this may be 100, this is 200, let us say 100 second, 200 second, I am putting arbitrary number. And if you go down further, you may find that it has come down, this is 50, this is 100. If you come down further, maybe it is 25, this is 50. If you go down again, you may find again it starts increasing. Somewhere you find that again it becomes 50 and 100. And then again say suppose it becomes 100 and 200. I am putting these numbers arbitrarily. This will depend on these are not the exact figure, I am just putting some arbitrary value. Now, let us say from this let us try and construct a diagram. Now, here let us say this temperature is the eutectoid temperature, that is let us say 723, and in phase diagram this is also represented as a temperature called A1 temperature, critical temperature A1. Now, let us say this is the temperature here. Now, at let us say 700, this temperature, these let us draw, this is start, this is the finish point. Similarly, here this is the start, this is the finish point. Similarly, another temperature we have seen once it starts decreasing, then again it starts increasing. So, this is the way it goes. And then if you join all this T s, so these are T s points, then you get a line like this, and you will also get another line by joining. These are, this represents time of completion of perlite, completion of formation of perlite or perlitic transformation. So, this portion of the diagram here you have gamma. So, what you really have, you are cooling it, say suppose we visually look at what we are doing in this case. We are cooling it like this, then holding it for some time. So, this is, let us say this is 100, the transformation starts and then it is completed here and you get perlite. Similarly, in the second case you are cooling it here and you are holding your several samples. Some of the samples you have cooled from here. We will see what happens in those cases. And then after it comes here, then the perlite transformation starts and here it is completed. And perlite, you know, it is made up of ferrite and cementite, and this is in between what you have, you will have a mixture of austenite plus perlite. We also look at what happens if some of the things we quench from here, what will be the structure. Same thing here as well, we will see here if you hold, this is the start, this is the finish. Here also we get a similar ferrite carbide structure, but what happens when we cool? There is a temperature, say somewhere here. If it exceeds this temperature, we call this temperature MS. We get a totally different type of microstructure, and there is a similar term MF. So, these are temperature. This calls the martensite start temperature. M stands for martensite. Now, we know that austenite is a solid solution of carbon in iron. All carbon which are there, they are present in the interstitial sites, and if you quench and you do not allow this carbon to precipitate out, so carbon is retained by force in the microstructure. Then you get a different lattice structure altogether, and this structure, see, austenite is face centered cubic and martensite, it is called body centered tetragonal structure. And in fact, this deviation from body centered cubic structure is very little. So, one can also assume as if it is a distorted, a little distorted body centered cubic structure. We will talk about it later in other lectures as well. We will come back when we go to different subsequent chapters also. So, it is a distorted lattice. So, if you retain carbon, say if you have a lattice structure and we know that diameter of carbon atom is little more than the interstitial site present, and we also have seen in the last class that interstitial site, particularly in BCC, that octahedral site, it is not symmetric. Two direction you have, the gaps are different. So, if you want to keep this carbon atom in the lattice site and still retain the structure as BCC, what happens in one directions the lattice increases. So, that is the C axis. So, we have say in a BCC structure, in a BCC lattice, A and C they are equal. In a BCC, distance, atomic distance along the C direction and atomic distance along the A directions, they are same. Now, here if your carbon atom is over here, if it pushes this apart rather than the other directions, it has enough space to accommodate, but in this directions, say in this direction it has enough space to accommodate, but this direction is shorter, this gap is shorter. So, therefore, in that so in this direction it is shorter. So, therefore, what will happen, this parameter will increase and what you have C by A will be little greater than 1 in case of a BCT structure, whereas in BCC this is 1, C by A ratio is 1. So, in one way one can assume that this martensite is a supersaturated solid solution of carbon in alpha iron. Now, let us look at now if we compile this diagram, what do you get? So, this is the type of diagram what you will get here. This is the A1, that critical temperature, above it, it is totally austenite. This is the perlite decomposition begins. This line represents the time. So, if you cool it at a isothermal temperature, different isothermal temperatures, this is the time you have to allow for this transformation to start, and this is the time when the transformation is complete. And if you keep the steel at this temperature and allow the transformation to be complete, you will get a coarse perlite structure. Exactly it is lamellar structure, but spacing is wider, and if you go down, then diffusion distance decreases, lower temperature diffusion distance will be smaller. So, you get a fine structure, fine perlite structure, and if you quench, you get a martensite, and in case of a martensite there is no diffusion, carbon atom does not move. So, this transformation is very fast. So, while the paralytic transformation is diffusion control, formation of martensite is diffusion less transformation. There is no diffusion of carbon atom here, and martensite. So, that is why if you are retaining carbon atom by force in the solid solutions, its hardness is very high, and that hardness it becomes almost the maximum hardness that is possible around 64 RC, that is what you get if it is 100% martensite. And so, from here where you have martensitic structure and a coarse perlite, which is the softest structure. The next diagram, I think we have put down the values of the hardness. If you have a coarse perlite, hardness is in this range, fine perlite hardness is in this range. You have a little different structure, this is also ferrite plus carbide, but the way the carbides are present, they are not long plates of cementite, these are broken cementite plates, but very much similar, closer to lamella. whereas in this particular case this carbides are still finer and the shape of this ferrite grain where this carbide precipitates is little needle like type of structure. That is what happens in this particular case, and this type of structure, this one is called bainite, and bainite you have two classification. In the previous one we name it, which is closer to paralitic structure, we call this feathery bainite. It only depends on if in the optical microstructure, that structure is so fine it will not be revealed in optical microstructure, but in ACM or TEM if you look at that microstructure you do see the nature of carbide and these platelets are broken, and that can be seen. And similarly, the nature of this austenite the ferrite grain and its morphology can be seen very clearly in electron microscope. And martensite structure, it is a single phase structure, it is a phase, whereas perlite and bainite you can't call them phase, they are mixture of two phases, whereas martensite is a single phase, and here you have much more than equilibrium amount of carbon present in solid solution, and that makes this structure very hard, and it is the strongest phase that is possible the bulk phase that is possible in conventional steel. And let us now look at the nature of this structure, what it looks like. Perlite we have seen, say what happens in the austenite, these are the austenite grains. So, you have this austenite grain, and so here perlite starts forming a cementite nucleus, then these are cementite and white region is ferrite. So, this is how the perlite structure will look like, they will be lamellar, and this is how that entire area will be filled up. And only difference is here you can see that optical microstructure, you may see that these perlites they are resolved, whereas in this case if this is that these distance between these plates will be so small that it will be difficult to you may see that it is a very dark region this type, and if you look under they will resolve and show that this type of lamellar structure. If you look under high magnification electron microscope, but essentially they are also made up of exactly similar lamellar structure, only the distance between these platelets plates are very small, and they are so closely spaced that you can't see these plates clearly. Now, in case of a bainite, what you have is say suppose here we say that this is an austenite grain in the structure, and when bainite starts forming, what happens here that mind you this is takes place at a temperature is high, temperature is high, temperature is high, whereas here the temperature is low, and we know that diffusion distance is proportional to root over dt, that diffusion distance is proportional to root over dt, and lower temperature the diffusion this d value is very small. So, therefore, that carbon atom will not be able to move over large distance to form this type of a lamellar structure. So, what happens here? So, you have this cementite, these are broken like this, they are not, say this is a ferrite grain and these are broken. So, this is another. So, this type of broken carbides you will get in that ferrite grain. and the structure is very fine, and what I am drawing here is a very enlarged view. An optical microscope, it may look very much similar to this. It will be extremely difficult to distinguish between fine pearlite and feathery bainite, whereas in acicular here also this transformation always takes place, starts near the boundary, and here whenever a sometime it is say sometime this type of ferrite grains are formed, and here you have carbides, and these carbides are differently aligned. Here it is along the grain, and here it makes a particular angle, and here. So, it may have several this type of structure. So, ferrite has a typical needle like feature, and these carbides are like this, and this carbide here, although it is cementite, same as in pearlite, and here this is called a different carbide. Its carbon content is little different. It is called epsilon carbide. This is, you can say, this is a metastable carbide, and in martensite structure is also an extremely fine structure, and here also the structure is a needle like structure, and this growth takes place very fast. So, that means once a needle forms, it extends over the entire grain boundary. It forms, it goes through this, it cannot cross the boundary, and this is the way the structure develops. So, entire structure gets converted into this type of needle type of structure, say this type of, and they are so fine, this normal optical microscope, and it will be very difficult to etch also. When you etch this steel, polish and etch, etching actually attacks these boundaries, and here such boundaries are not existing, that carbide boundaries are non-existent. So, it is little difficult to etch, and later on we will see when we look at heat treatment, if you give a little tempering treatment, then they etch very easily, and when that carbide precipitates out in these platelets, these are called needle like, they are all BCT structure, each has its own character, that is a different orientation, and we name it as alpha prime, and this is called martensite, and it has a body centered tetragonal structure. And if we go back now, look at this structure, what is happening in a martensite, where you are not allowing the carbon to come out, and the structure is the fineness, and this is where it has the maximum strength, whereas the coarser structure you get in this region. So, coarser structure has lowest hardness, finest structure is the martensite. In between you have a mixture of pearlite, and in between you have a mixture of coarse pearlite, fine in between at this intermediate isothermal temperature, the microstructure changes from coarse to fine, feathery, acicular bainite. As you go down that isothermal temperature, the structure becomes finer and it becomes much stronger. And if we look at this, and what happens if you quench in an intermediate fashion. Say suppose, let us look at this diagram, what type of structure you will get here. Say suppose we have seen that when you quench like this, you get 100% martensite. So, here the hardness is maximum, but when you come here and hold it and then you cool, in that case what will be the microstructure? Here that microstructure you can visualize like this. You have, once this point exceeds, you have these nodules of perlite forming. These are nodules of perlite have formed, and then rest of the thing, if you are quenching, here you do not allow time for the carbon to diffuse and form and continue with the process formation of perlite. So, here what will happen? You will have this type of a needle like structure. This type of needle like structure you will have. So, this is martensite. This is martensite. So, what structure you have in between is a perlite plus martensite structure, and depending on the temperature, it can be coarse perlite or fine perlite. Similarly, if you quench something here, hold it and from here you quench, in this case the structure will be in the same way. You have colonies of bainite forming and rest portion will convert into martensite. So, the structure is a mixture of ferrite and martensite. So, that is why here when you measure hardness, your hardness is in between martensite and perlite, and if the transformation is the highest temperature, that lowest hardness that you can get is around this. If your transformation temperature goes down here, so that is why if you go back and see that lowest minimum hardness goes on increasing as the temperature decreases. And later on we will see this can be extended, this concept can be extended to continuous cooling. So, normally this type of isothermal transformation is difficult to conduct. So, and it is also possible to use this type of diagram to interpret what happens when you cool it structure slowly and when you cool it fast. Here also this concept is very useful to understand effect of cooling rate on the formation of microstructure in steel, and this we will come back later when we talk about heat treatment of steel in a subsequent chapter. So, therefore, we now finish that iron carbon system, and mind you we have only looked at binary iron carbon system, and if you have a third alloy element, the phase diagram will alter. So, also the time temperature transformation diagram will also change, and all these we will take up in subsequent lecture. To sum up, in these two today we looked at iron carbon phase diagram, and we have seen what happens, how the diagram modified if a stable graphite phase forms in the structure. We looked at gray cast iron. We looked at effect of carbon on properties of iron carbon alloy. We looked at eutectoid transformation, of course, a qualitative explanation of eutectoid transformation, and we looked at the importance of the temperature in determining the microstructure of the transformation product. We talked about time temperature transformation diagram, and we also learnt about two different types of microstructure that you can get depending on the transformation temperature. One is bainite, which is little different from perlite, but it is also mixture of either a carbide called ferrite cementite, or it is ferrite plus epsilon carbide, and we will later on we will get opportunity, we will talk about it in detail when we take up heat treatment subsequently at a later date. Thank you very much.